listening side has two core elements: lookup transform and can transform. Lookup transform will simply will return to you the transform between the coordinate frame that you requested and the target coordinate frame. There are some slightly more advanced versions that I'll talk about a little bit later. But in general, basically, lookup transform will compute the traversal across that tree. Can transform is a slightly lower cost computation, and it will tell you whether or not you can transform from one leaf of the tree to another. And that is used if you're trying to do things like test whether or not the data is there. If you call can transform, you can do that a lot faster and poll on that, and then you can call a lookup transform. In general, you probably won't actually have to call these methods themselves. They're in the core library, but I need to explain them to you so that you can use the higher level ones. So how do these two methods work? This is a fun, basic tree. It's a little simplified. If you think about the PR2, there's 35 frames up on this tree. I can't fit those onto one slide, so I've simplified to this simple one. But if you look at this, say the laser on robot 1 is producing data, and robot 2 wants to navigate based on it. Now, to navigate based on it, you're probably going to work in your either odometric frame or in the map frame. And so when robot 2 receives a laser scan from robot 1, you will want to compute the transform from the laser to the base, from the base to the odometry, odometry to map. And say you're planning an odometry, you want to go actually back down to the odometric frame. And the call to lookup transform, you will simply say, look up the transform from robot 1 laser to robot 2 odometry, and it will compute the inverse transform up and then the forward transform down. Be careful, forward transforms and inverse transforms, depending on how you view it, the transform from a frame to another frame is the inverse of the transform, vice versa. But if you're talking about applying the transform to data, it's one way. And if you're talking about transforming the coordinate frames, it's the opposite. So what is actually happening in each of these links is that the listener has a linked list of all the data it's heard in the last 10 seconds between each of these frames. It will take the timestamp at which you are operating and compute the closest transform. It'll interpolate between two things. If you've got it at time 0 and time 1 and you ask for it at time half, it'll do interpolation. And it does that for each link in the tree. And if you're doing robot 1 laser to robot 1 camera, so you want to do some laser to camera calibration, you will simply it will just return the product of these two. In its search, it does do a depth first search, so both of them will go all the way up to the top to map, but then it will prune back before it does the computation. Sorry, and can transform will simply do it and return whether or not true or false. So what you will actually end up using most of the time are the helper methods. These are basically methods that will both take in the data, read the transform the header, and read the header to get the timestamp and the frame ID, and actually apply the transform to your data. They use pass by reference, and they will return. So you pass in as pose stamped, and you get back a pose stamped in the case of pose. These are defined on the basic data types inside of ROS, both for messages and the TF data types. And there are bindings for various data types like KDL ones, eigen, and point clouds. So one of the most complicated things about TF is keeping things synchronized. Because you're working in a distributed system and you need both your data to be available and the transform data to be available to transform that data into whatever frame you want, you have to be able to wait for one or the other. The way we do this is that we have, there is the very simple method, wait for transform, which will do exactly what it sounds like. It will block until the transform for that data is available. The other one is a TF message filter. It will automatically do this for you, where it will receive a message for you, store it in a buffer, and provide you with a callback when the transform into the frame that you want is available. I strongly recommend this, and I'll come back to it. So for the wait for transform, I want to point out a couple of dangers. If you have a single-threaded process and you call wait for transform will always fail if it fails the first time. Or if it doesn't work immediately, it will go all the way till its timeout, because there's no new data coming in on another thread. In general, this can lock up your system for a long time. Another thing is that if you're using wait for transform on streaming data, if there's a lag in your TF data coming over wireless from another robot or something, and you have to delay by 1/10 of a second, your entire process will fall behind by 1/10 of a second the first time you call it. And after that, wait for transform will be very quick, because the whole process is 1/10 of a second behind. So if you're having latency issues or worried about latency, I do not recommend wait for transform. However, it is very, very convenient if you're just scripting something. If you get data in, you want to process it once and send it out, it's very convenient. So the message filter is the designed alternative for doing this wait for transform and delaying your whole process. As I said, what it does is it'll actually subscribe for you and store your data and give you the callback just like you subscribe to it, but it will have made sure that the precondition is valid, that the data can be transformed into the frame that you want it to be in when your callback is called, which means that you can make the assumption when your callback's called that the transform is available. This does not mean that it's still good practice to put it in a try-catch block, because there may be other problems, or it may go out the back while you're processing.